Hey everybody, in this video we're going to talk about using double angle identities. So we've already gone through the process of finding the double angle identities for cosine. We've got those in the middle of the screen here. And for sine on the right. And then we also have our basic identities that we have for tangent equaling sine over cosine and the Pythagorean identity of sine squared plus cosine squared equaling 1. So all of these can be used to find values that would fall somewhere on the unit circle. And a lot of these things we don't even need to know what the angle measurement is to find that now that we have these various identities. So we're going to look at some examples and see how these things might apply. So let's throw one out there. Given that sine x is equal to 3/4 and x is between 0 and 90 degrees, find the exact values of cosine x, sine of 2x, cosine of 2x, and tangent of 2x. Okay, so first thing we should do when we think about this is think about how does this work with the unit circle. And unfortunately 3/4 is not one of those key values that we use on the unit circle. So that's not going to really help us other than remembering what the relationships are within the unit circle. So we had to find another method. Cosine x is not using any of the double angles. So we can basically wipe out that whole from the middle on. We don't need to look at any of that. And we don't need tangent either. We don't have tangent. All we have is sine. So the only thing listed here that could help us is this Pythagorean identity. So all we're going to do is we're going to plug in 3/4 into the equation and we'll solve for cosine x. So 3/4 squared plus cosine squared x is going to equal 1. So now we're just going to solve for that cosine x, right? So we're just going to keep on plugging away. So 9/16 plus cosine squared x equals 1. Bring our 9/16 to the other side, so cosine squared x equals 1 minus 9/16. Cosine squared x equals 7/16. We don't want to know what cosine squared is, we want to know what cosine is, so we've got to take the square root of both sides. And we're left with cosine x equaling plus or minus the root 7 over 4. Now, we're saying plus or minus because we've taken the square root of an unknown value. We don't know what cosine x is. So if we've got cosine squared x, that's still an unknown value, so when you take the square root, you have to look at the positive and the negative possibilities with that. However, our original problem states that x is between 0 and 90 degrees. And that tells us that both the sine value and the cosine value is going to have to be positive in there. So because we're in the first quadrant and both values have to be positive, we can ignore that negative value and we'll just have positive or root 7 over 4. And we're good to go with this one. All right, so what about sine 2x? Well, sine 2x, we're going to use the only double angle identity that we have, 2 sine theta cosine theta, or 2 sine x cosine x. So we can just plug in the values that we have. So 2 times 3/4 from the original problem, 3/4, and then our cosine x, root 7 over 4, which we just found. Multiply this together, and we can cancel out the 2 and the 16, and we'll get 8. So we end up with 3 root 7 over 8, and there's our sine 2x. All right, what about cosine 2x? Well, cosine 2x, we could really use any one of these three values because we already know what cosine is and we already know what sine is. We found cosine in the first part, sine was given to us in the original. However, it's always a good test-taking strategy or any kind of problem-solving strategy to use the values that you were originally given. So in that case, we're not going to want to use the cosine values, but we're going to want to focus on one that just has sine, because that was in our original problem. So we'll use this top one, 1 minus 2 sine squared. So again, it's just going to be a plug and chug, just kind of throw some numbers in there and see what we get. So 1 minus 2 times 3 over 4 squared. So we got 1 minus 2 times 9/16. We can do some simplifying and get 8 down here, so 1 minus 9/8, or a negative 1/8. And that's our solution. Now, before we said, hold on, cosine, it had to be positive, so because we're in the 0, between 0 and 90, we're in the first quadrant. But double angles can span across multiple quadrants. So even though we don't know what the value of that angle is, we could get a negative cosine of 2x and a positive value for cosine of x. So that's okay. So that one we don't have to restrict or do anything different. All right, let's look at the last one, tangent of 2x. So tangent of 2x, we've only got one possibility for tangent of 2x, and that's going to be our original identity, sine theta over cosine theta. And we're just going to, instead of use sine theta and cosine theta, we're going to use sine 2x over cosine 2x. It's all still proportional, whether it's a double angle or not. So we can do this and have these two values, the ratio of these two values. So we'll just plug them in. So we've got our sine of 2x is 3 root 7 over 8, and our cosine of 2x is negative 1/8. So throw the sine in the numerator and the cosine in the denominator, and we've got ourselves a nice complex fraction. So remember, we have to, when we're dividing by a fraction, we multiply by the reciprocal. So I'll have 3 root 7 over 8 times negative 8 over 1. Do some simplifying, and we're left with negative 3 root 7. All right, so that's one set of problems that you might have. Let's look at another one. So let's just put this out there. So solve the equation sine 2x equaling sine x for x between 0 and 360. So a full rotation around the unit circle. All right, so what are we going to do with this? Well, let's start our working up here. Let's first get everything on one side of the equation. So we got sine of 2x minus sine of x equaling 0. Now you could have done some reasoning and found the values for sine of x where that equals sine of 2x, but it's not necessarily going to give you all of the possible answers. So that's why we're going to do some algebra here, some trigonometric algebra to find that solution. Okay, so now we've got sine 2x and sine x, and we don't have any values for anything. So let's see if we can get this to not where we're talking about a double angle, but just a regular angle of sine x. So what we can do is we can substitute in 2 sine theta cosine theta, or 2 sine x cosine x, for our double angle here. So we got 2 sine x cosine x minus sine x equaling 0. If you notice, we've got two common values here of sine x, so we can factor that out, and we're left with 2 cosine x minus 1 equaling 0. So this is actually similar to a quadratic factoring that we've done, and when we did that, well, we would say, well, either sine x has to equal 0, or 2 cosine x minus 1 has to equal 0 for this whole thing to equal 0. So now we can solve each one of these and see what kind of solutions we come up with. So let's start with sine x. Oh, sorry, but even before we do that, cosine x, if we solve for cosine, get cosine by itself, we're left with 1/2. So we just added 1 over divided by 2 and got cosine x by itself. So now let's take a look to see what values we have. So sine x equals 0 at 3 spots as you go around the unit circle from 0 to 360. It happens at x equaling 0. It happens as we go around and hit 180 degrees. And then when we get back and we finish the full circle at 360 degrees. Cosine x equaling 1/2 happens in the positive x half of the unit circle, which is in quadrant 1 and quadrant 4. So where cosine x equals 1/2 in quadrant 1 is going to be 60 degrees. And then as we continue around and get to where that same value is on the unit circle in the 4th quadrant, we'll get 300 degrees. And these 5 values are our solution for this problem. All right, so I got one more problem. It's a kind of a proof type problem that you might see. And it looks like this. Prove that 1 plus tangent squared x cosine 2x equals 1 minus tangent squared x. All right, so there's a couple things that are happening in here. And when we're asked to prove this thing, we have to look at one side and try and get it to the other. We're not going to be shifting things from one side of the equation to the other. We're just going to pick either the left-hand side or the right-hand side to solve this thing to break it down from the left-hand side to get to the right, or from the right-hand side to get to the left. I always think that it's easier to make an equation smaller than to make it bigger. So I'm going to go with the left-hand side of this equation. Now when I'm looking at this, there's two things that are jumping out at me. I've got cosine of 2x, so I've got a double angle, and then I also have, and I'm trying to get it to be a tangent squared x. And I've already got a tangent squared x over here, but when I start substituting things in for cosine of 2x, I'm going to be getting all these sines and cosines. So what I want to try and do is get this so I've got a common language across. And the best bet is to convert everything into sine and cosine. So that way you're all working on the same level. If I kept this in just tangent squared on the left, I might forget that I've got that value of sine over cosine, or sine squared over cosine squared. So it's good to kind of break everything into sine and cosine values. So let's start by breaking out this parentheses to sine squared x over cosine squared x, 1 plus that. Now we have to pick which of our 3 cosine double angle values to use. Now, we could use any one of these, but some are going to lend us to a better place than others. And so actually it really is only going to be one that's going to be the most helpful for us. And if we think about what we're about to do, we're about to plug in either 1 minus 2 sine, 2 cosine minus 1, or cosine minus sine. So all of these things, if we drop it in for our double angle, would give us something that looks like 2 binomial factors. So like again, going back to our quadratics, we'd have x plus 1 and x minus 1. And we'd have to multiply all those parts together. We're basically going to have the same thing here. Now, if we have a sine squared in there, when I'm multiplying this around in all my different parts, I'm going to end up with something sine to the 4th power, because I'm going to have to multiply it by this fraction where in the numerator I'm going to have a sine value. I don't know how I'm going to break down a sine to the 4th value. So I'm going to jump and I'm going to use the one, so get me to the 4th power. So I'm going to exclude those and I'm going to look at the one that just uses cosine. Because if I look at that, I know at some point this fraction is going to start simplifying and I'm going to knock out a couple cosine values. I might be left with a cosine and a sine, but let's see where that takes us. So I'm going to plug this 2 cosine squared x minus 1 in for that. So now I've got to multiply all my parts together. So 1 and 2 cosine squared x is 2 cosine squared x. And then I've got 1 and negative 1, so that gives me a negative 1. Then I've got the fraction sine squared x over cosine squared x times 2 cosine squared x. So 2 cosine squared x is going to go to the numerator along with our sine x. So 2 cosine squared x times sine squared x, excuse me, over cosine squared x. That's good. I know I can cancel some stuff there in a second. And then the last thing is multiplying these two last terms, so I get minus sine squared x over cosine squared x. All right, so we can simplify, knock those cosines out, and we're left, and this thing here, it looks like it could turn into a tangent, which is what we're looking for up at the top on the right to get to the right-hand side. But I don't know if I'm going to need to use these sines, the sine squared and the cosine squared yet, so I'm not going to convert it into a tangent just yet. We could, and then we could always convert it back out, but I'm just going to hold on for a second. So let's rewrite this. So we got 2 cosine squared x minus 1 plus 2 sine squared x minus our fraction. Now, because I've done this a little bit, some things are jumping out at me a little bit more than they might be for you. But if I rearrange this a little bit and I bring these cosine and the sine squared together and bring them next to each other, I can see that I'm going to start having something that I can substitute in there. All right, and then we'll just bring the rest of it along as well, the negative 1 and the negative fraction. So as I'm looking at this, I've got a common factor of 2. So I could factor out a 2 from the cosine squared and the sine squared, and that would leave me with cosine squared x plus sine squared x, and then I'd have minus 1 minus our fraction. And cosine squared x plus sine squared x, well, that whole thing is going to equal 1, right? Just like we had from above. So we've got 2 times 1 minus our fraction. Now we can see, okay, we can put this into our tangent squared, and our numbers are going to cancel each other out. So we've got 2 minus 1, so we have positive 1 minus our fraction here, so we can now convert it to our tangent squared value. And we get to the given value on the right-hand side, and we have proven that these two things are indeed equal. So this is a way that you can use all these identities and substituting values in and reworking it and simplifying to show that one complex thing is equal to another. Now again, we could have gone from 1 minus tangent squared x up to the other value, but it might get a little bit more complicated because we'd have to start plugging in things for just one, and that might be a little bit more complex. So I like to go from the bigger side to the smaller side. So anyway, I hope that helps with some of the things that you've been working on, and we'll talk to you in the next video.